Okay, so 42 asks about um, ionization energy. Okay. Um, and so it's in topic 2 of the HL, but it also relates to topic 3 because topic 3 is where we learned about all the periodic trends, which includes ionization energy. So you might have to refer back to your topic 3 note SL notes to maybe help with this. But why is the first ionization energy of oxygen higher than the first ionization energy of beryllium? So it basically, what it has to do with is their locations on the periodic table. So I'm going to switch over and so this is not y'all's periodic table, but it's a periodic table. And so what I want to do is look at where they're located. So beryllium's over here, oxygen's over here. So they're both in the second period. It means they both have 2 energy levels that have electrons on them. Like if I were to draw their Bohr models, beryllium would be like this, and then the second energy level would just have 2 because it's 1s2, 2s2. And then if I did oxygen would have the first energy level 2, the second energy level would have 6. 1, 2, 3, 4, 5, 6, because it's 1s2, 2s2, 2p4. Okay. So you don't have to draw all this stuff. I'm just showing you guys this to explain it. But what it really is it's their location on the periodic table. Okay. They're both in the same period, so they both have 2 energy levels. And so what you have to look at is when we learned last year in topic 3 is that as I go across the period left to right, the ionization energy increases. And so as you go across left to the right, the ionization energy increases. And the reason that it increases is because as we go across, the nuclear charge increases. Because beryllium here in its nucleus, it's got 4 protons because its atomic number is 4. Oxygen here in its nucleus, it's got 8 protons because it is atomic number 8. I almost wrote 6. I was thinking valence electrons for a second. So the difference is, look at their Bohr models. They both have 2 energy levels. So you would think they're like about the same size, but really oxygen is a little bit smaller because it's got more protons in the nucleus that are attracting the valence shell here. So as you go across a row or across a period, what happens is because you're adding more protons in the nucleus, but any electrons are just being added to the same valence energy level, it causes the attraction between the nucleus and the valence shell to increase. And that causes your atom to get smaller. So your atomic radius decreases. And since the valence electrons are closer to the nucleus, they're attracted more because that nuclear charge is going up. That causes the ionization energy to increase because ionization energy, as we learned last year in topic 3, is the amount of energy required to remove a mole of electrons. Okay. And so the smaller your atom is, the more attracted the valence electrons are to the nucleus, and therefore it's harder to take them away. So it's a higher ionization energy. So this question, to really all they're looking for in terms of an answer on this is they're looking for you to say that oxygen has a higher nuclear charge, which attracts the valence electrons and makes them require more energy to remove. Okay. But the big explanation is kind of what I'm showing you, and it has to do with the fact that they're the same number of energy levels, but more protons are attracting that valence shell. So it pulls it in closer and holds it more tightly. And that means it requires more energy to try to take one of those electrons away.
Okay.
Okay, so like as we go through stuff now, y'all are gonna see that like our topics are gonna overlap a lot more. Like that was technically it's here in the HL of topic 2, but really it relates a lot to topic 3. So we're gonna see like as we go through more stuff and we get closer and closer to like finishing everything, we're gonna see that like everything's gonna kind of intertwine, and there's gonna be some questions that are gonna require us to like think about different topics. So even though we learn the topics kind of in isolation as we go through now, get closer to May when you guys take your test, We're going to do more of these questions where you're going to have to think of like all the different topics kind of, and that's because that's how a lot of the questions are on paper 2 on the open-ended questions, is there'll be multiple parts, and it'll be like part A is like asking you about atomic structure, but then part B is asking you about a trend, and then part C is asking you about something with stoichiometry, and then part D is asking you about something that's, you know, acidic and basic, or, you know, it's all kind of intertwined like that. On 44,
I had a question with the last two, with the copper and gallium.
oh, okay. So copper is, I think copper is one of our exceptions, but okay, so start off, let's just do their regular electron configurations. So for gallium, where is gallium? Gallium is 31. So 1s2, 2s2, 6, 3s2, 3p6, 4s2, and then 3d10, and then 4p1. Okay, so I'm doing gallium right now. So this is, if I just did the regular element gallium, this is what I get. Okay. For the ion, if you look here, it's got a +3 charge here. Okay, that means it's lost 3 valence electrons. Okay, so remember, what's the definition of valence electrons? They're the electrons that are in the highest energy level. Okay, so D and F electrons are never going to be valence electrons. So if you look, the highest energy level here, it's the 4th energy level. Okay, you got S sublevel and P sublevel, but they're both in the 4th energy level. And look, there's 2 here and 1 here. So those are the 3 that it's going to lose. So when you rewrite it just for the ion, it's those 2 just disappear. So you have 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d10. Because it's lost everything from the 4th energy level, those 3 valence electrons. Copper, it's going to be the same, but if you remember from last year, copper's electron configuration, copper is one of our exceptions. I think it's copper and chromium. Yeah, copper and chromium are the 2 we learned last year that their electron configurations don't follow the rules. Okay, so normally copper would be 1s2, oops, 2s2, 2p6, 3s2, 3p6, 4s. So if copper followed the rules, it would be 4s2, 3d9. Okay, if copper followed the rules, that's what it would be. Okay, but copper doesn't follow the rules because if we look at the orbital diagrams, if we look at like what its 3d would look like, if we do 9, we do 1, 2, 3, 4, 5, 6, 7, 8, 9. Leaving this last one only half full is actually less stable. So because 3D has higher energy. And so what happens is one of the electrons here in the 4s, it gives it away and it comes here. And so it actually ends with 3D10, and then the 4s changes to 4s1 because it's more stable for the 4s to be half full than for this orbital on the 3D. And so it's one of the ones that doesn't follow that rule. So normally that's what it would look like, just the element. Now, if it's Cu that's lost 2 valence electrons, then what's going to happen is it's also going to do like we just talked about, where it loses the outermost, the highest energy level. So it's going to lose this one right here because that's the 4th energy level. And then the next one that it would lose would be one of the ones from here. So then it would be 1s2, 2s2, 2p6, 3s2, 3p6, and then it would end with 3d9. And so now 3s2, 3p6, those are going to be its 8 its valence electrons. Anybody else have questions?